We're going to see many of the tests that showed us that limits converge also work for these improper integrals for good reason, because they're limit processes that are dictating whether these improper integrals make sense or not. The first is the comparison test. And this is maybe the single most important test. This is a test that we're going to see over and over and over again in a lot of contexts. And maybe you recall this from AP Calculus. But we'll state it here, and then we'll see some examples of it in use. So suppose that we have some function that's at worst 0, so it's positive or 0, and it's always less than or equal to some other function g. And this is for all x in some domain. We'll say the domain is greater than 0. It's not strictly important that this is 0, it just has to be some lower bound. Then the comparison test says the follows. It says two things. One, if the integral, or the improper integral of this larger function is convergent, then the improper integral of the smaller function also converges. Additionally, it says the contrapositive. So if instead of the bigger function still managing to converge to a real number, it does not blow up to infinity, then the smaller one also does not blow up to infinity. The reverse is true. If the smaller function does blow up to infinity, diverges. If the smaller function blows up to infinity, then so does the bigger one. If note that the converse and the inverse of this, meaning if I just said if the bigger function diverges, if the function that's always bigger blows up, we don't have any idea how the smaller function behaves. It might blow up, it might not. And conversely, if the smaller function converges, if the function that's smaller actually converges to a real number, we don't have any idea how the bigger function behaves. The bigger function might converge, the bigger function might blow up to infinity. But if in these cases bigger shrinks is stabilized, then so does the small one, or the smaller blows up, then so does the bigger. Before we do a few more examples, I want to state one more theorem that's related to this comparison test, which is more formally known as the absolute convergence of an improper integral. This is more, I guess more informally, this is like a worst case scenario theorem. Like this is looking at the worst case scenario. What I mean by that is that it says this, that we look at an improper integral of the absolute value of a function, if you put absolute value around a function and it still converges, then the original function definitely converges. I refer to it as the worst case scenario because think about what does absolute value do to a graph. Absolute value to a function makes every value positive. So if you didn't have this, sometimes you'd have situations where you have positive areas above the curve, or maybe the curve dips below the x-axis, and you have negative areas. So in situation where there's no absolute value, then sometimes those positive areas and those negative areas could add and cancel, keeping in a real sense, keeping the overall area not blowing up to infinity. If, however, you slap absolute value around it, then every area is positive. So this removes the situations where you can have those negative areas canceling out some of the positive areas. This theorem says that if you're in this situation where even if you make everything positive and this function still converges to a real number, if it still doesn't blow up to infinity, then in this case, in this worst case scenario, if this situation is true, then you definitely know that if you let some of the areas cancel some of the other areas with the adding and subtracting, then that's definitely not blowing up to infinity either. So this idea of absolute convergence is something that's going to again rear its head both in the world of integrals and as we're going to see in the coming lessons in the world of infinite sums. So we're going to take advantage of both the comparison test and the idea of absolute convergence here to analyze some improper integrals that maybe are a little bit that maybe at first blush are a little bit outside of the realm of our of comfort. So we're going to use integration by parts and the comparison test to prove or to show that this integral from 1 to infinity of sine x over x dx actually converges. So if I'm going to use integration by parts, I really need to have a product of two functions here. So I don't really want a quotient. I'd really rather have this product. So note that 1 to infinity of sine x over x dx, really that's the limit as b approaches infinity, 1 to b sine x over x dx. Maybe it's worth noting at this point, it may seem like a pain to rewrite the limits from infinity to a limit that approaches infinity. It may seem, maybe it seems to you, because it does to me, when I'm just working through the problems, like it's just an extra step that's getting in the way. Both the IB exam and the AP Calc BC exam, in order to earn full credit on any of the questions, it must be present that you recognize that you've rewritten improper integrals as in a limit statement. If you do not do that, you will not earn full credit on those questions. So make sure you take the time to actually do this at some point, sooner rather than later in the problem, in my opinion. But you definitely need to do this. Need to do it at some point if earning full credit on the questions is something you're after, which I hope you are. I'm going to rewrite this as a product. Instead of sine x over x, I'm going to do this. How about sine x times x to the minus 1 of integral from 1 to b sine x times x to the minus 1. Let's see, what would make sense here for integrating this by parts? Remember our rule of thumb was we want pick u. U should be something that we know the integral of. U should be something that we know has an easy derivative, an easy to calculate derivative, or a derivative that gets simpler as you go. I think neither of these really become simpler, so maybe our choice of u isn't really that important. We should also we could then maybe look at the choice of v prime and think of what is v prime should be the function in here whose integral or antiderivative we know as well, and it should be in the most complicated function we know as well. I think in the world of that's complicated is pretty subjective, but I think that sine is more complicated than a polynomial. So with that, my intuition says that I think I'm going to go with this is my v prime and x is my u. This analysis might work the other way. I've never actually tried it. If you flip-flop the two roles, but so maybe give it a shot on your own. This is the way I've approached this problem, and I think it works out pretty well. So we'll say u is x to the minus 1. Therefore, the derivative of u is minus x to the minus 2. We're defining v prime to be sine. So that means v is the antiderivative of sine, which is minus cosine. So integration by parts, recall, tells us that the integral of u v prime dx is this is equal to uv. So x to the minus 1 times minus cosine. So this is, how about minus cosine of x times x to the minus 1, or how about over x? And we should evaluate this from 1 to b. Minus the integral from 1 to b of u prime v. So minus x to the minus 2 times minus cosine. The two minuses will cancel out, and we'll get I think cosine over x squared. And all of this is the limit b as it approaches infinity. So note, we can evaluate this guy. This is just minus cosine of b over b minus negative cosine 1 over 1, so plus cosine of 1, we'll say over 1, how about that, minus this integral from 1 to b of cosine dx. And again, limit is b approaches infinity. So how can we handle this? First, note that that cosine is always stuck between negative 1 and 1. So in particular, cosine, well, I guess that minus 1 is less than or equal to cosine of b, and is less than 1 for all b. Namely, if you put this in absolute value, this is cosine b is less than 1. So I think as b tends to infinity, this is some number that's between minus 1 and 1 over infinity. So I think this tells me that this limit has got to be 0. Cosine 1 is a constant, so this is just cosine of 1. The question is, how does this behave? And more particularly, note that the question doesn't ask you to actually evaluate what this is. I don't care what the actual value of this integral is. I just want to know, and I just want to show that it's convergent. That in the limit, this does not blow up to infinity. This is just some regular old real number. It's not infinity. I already know that the first two parts are not infinity. The only question left is this new integral that we got from integration by parts going to blow up to infinity? And I think the comparison test says no. Because of this, note this says, this means that if you look at the absolute value of cosine that the absolute value of cosine x over x squared is smaller than or equal to is 1 over x squared, because, well, cosine is somewhere between minus 1 and 1. And if I put an absolute value, then I'll guarantee this is true. So that means that by comparison, that the integral from 1 to b of the absolute value of cosine of x over x squared is smaller than or equal to 1 to b of 1 over x squared. And we know that this does not, and also note that this has got to be greater than or equal to 0 because it's in absolute value. And also note that this guy is one of those p series, or p integrals. It's 1 over x to a power. And this integral, since the value of p is greater than 1, this integral converges. So namely, This is less than infinity by the p integral test. That we discussed in the first video. So what does this mean? So that means that that the cosine of x over x squared, this integral from 1 to b, converges as well. So put this together, what does this tell us? We have something that converges plus something else that converges minus something that converges. Since all three terms converge, all three terms converge, the entire integral converges as well. Proof complete. Okay. So I got one more example. Well, we're going to evaluate a sort of integral from any constant a to infinity of x e to the minus x dx. This sure looks like many of those examples of integration by parts that we saw earlier. So note that this integral is equal to b from a to b x e to the minus x dx. This screams integration by parts because there's there are two functions multiplied together, and I think by now pretty clear that u needs to be x. The derivative of this is simpler at 1. We'll call e to the minus x v prime because the integral of e to the minus x is easy. It's minus e to the minus x. So this says that this integral is really uv minus x e to the minus x. We'll evaluate that from a to b. Take away the integral of u prime v of 1 times minus e to the minus x from a to b, which is minus x e to the minus x from a to b plus minus e to the minus x evaluated from a to b. And all this is limit as b tends to infinity. So let's plug in the a's and the b's. I think I guess first note that plus negative e's. I probably should have just written this as subtract. Let's plug in the b's. So this is, note this is the limit of minus b e to the minus b, take away e to the minus b, and then let's plug in the a's, minus a e to the minus a, minus e to the minus a, or how about distribute the subtraction between these two, so as well. Adding, combine the like terms, or at least group the factor out the terms that are in common in each of these. How about minus e to the minus b, b minus 1. Plus e to the minus a plus 1. This is limit b as it has to infinity. Turns out that the term with the a's doesn't have any b's in it, so that's great. We don't need to worry about that in the limit. So we just need to figure out what is this. Does this blow up to infinity, or does this do something, behave in some other way? Note that this is the same as limit of b minus 1 I guess, sorry, b plus 1 over minus e to the minus b plus e to the minus a. What is this limit? Well, this limit is, if I plug in, if b tends to infinity, this is infinity over infinity. So this would be L'Hopital. When I use L'Hopital, the derivative at the top is 1 over e to the minus b, which tends to 0. Thus, the original integral from a to infinity of x e to the minus x dx is just equal to e to the minus a times a plus 1.